Can you see the screen?
Yes, ma'am.
So this part actually we have seen in last class that if there be a certain short circuit at any part of a transmission line or in a power system, then actually current will have a transient component and a steady state component. Okay, and transient component will die down with the passage of time, and it depends on the time constant of that circuit. So, and then we have plot the current variation for the worst scenario in the system. So, in that case, depending on variation of the current and the magnitude of the current, that means the severity of the fault, we can uh, divide the total duration of fault into three periods. One is subtransient, where current is very high, but it is decreasing fast, and second is transient period, when the transient current is there but it is decreasing in slower rate, but it is there. And in steady state period, when there is no transient current, only the steady state fault current is there. So there are two issues. If we want to save the circuit, it is better to disconnect the circuit as early as possible. So ideally after initiation of the fault, that is during sub-transient period. But at the same time, during the sub-transient period, current is huge. After first half cycle, it is twice of the steady state current, so disruption of the circuit will be difficult. So two issues are there when we design a protection system for a power system. Then we keep in mind these two things, and then we have to make the compromise. Okay, we cannot fulfill these two criteria at a time. Now, say if we want to analyze fault for a power system, then it is required to represent every circuit component by their equivalent circuit depending on their behavior during the fault. You must write your roll number around 145 or 150. Okay. So, let us represent the generator, find out the equivalent circuit of the generator during fault. Now you see the currents are not same, current passing through the generator supplied by the generators are not same during transient, subtransient and steady state period. Depending on that, behavior of the generator also changes. Let us find out that one at first. This thing I have explained, I have forgot to send you this slide. Today I shall send. So, this is the equivalent circuit of an alternator during normal condition. I have written here during fault because in this part of the presentation I shall discuss that one. But whatever I have drawn in figure 3, that is the equivalent circuit of an alternator under normal operating condition. That means voltage behind a reactance or impedance. What is the impedance? There are three components of impedance. Resistive part is the resistance of the armature winding. XA is representing the armature reaction of the generator, and XL is the leakage reactance of the armature winding. 1 minute. So, this is the equivalent circuit of the alternator during normal operating condition. And the armature reaction reactance and the leakage reactance altogether is called the synchronous reactance. I hope you know that. And total resistance and reactance altogether is the impedance. But generally we neglect resistance during fault calculation because the role of resistance in controlling the fault current or the armature current is very less as compared to the reactance. So generally we neglect the react resistance. But if we want to get the actual calculation, actual scenario, we should consider this. You should come in time. I do not allow after 1-5 generally. Within 5 minutes you must join. Then the air gap flux that is responsible to transfer power or generate power in the alternator, that is the air gap flux, right? You should come in time. You should come in time. Otherwise, it is very disturbing. Now, air gap flux is responsible to generate the power generate the power in the armature of an alternator or the three-phase power. So, air gap flux is the effective flux which is generating the electrical power from the mechanical power obtained from the turbine. So, that is the actually the field flux minus the armature reaction flux. So armature reaction, this is the normal operating condition. I have not told anything about the regarding the fault right now. So this armature reaction flux during normal operating conditions, some armature reaction flux will be there. Maximum will be the rated current of the alternator. Depending on that, that generator has been designed, and based on that, what will be the power, what maybe the design criteria is required, that is given, that is there. But when this fault current, this armature reaction current is converted to fault current, that means when there is a fault, then the generator is not supplying a normal current. It is supplying a fault current. I am writing IFL because IF is there for field current. Now this fault current is much higher than this armature current. Then now, actually, the during fault, the armature current is the fault current. So this armature reaction flux is now due to that fault condition. We may write this one IFL, or due to the current flowing through the armature due to that fault. Now this obviously this armature reaction flux in that case will be very much higher as compared to the normal flux. So what will happen? It will drastically reduce the air gap flux from its desired value. Now, every system has the tendency to maintain its normal equilibrium or normal operating condition. So, generator will also try that one, and um, to countermeasure sudden disturbance, there are damper windings in the armature winding slots. Damper windings are short-circuited winding that is present in the armature of the alternator. When huge current flows, then there is an induced EMF in the armature damper winding also, which produce the damper winding flux. And damper winding flux is produced in such a direction that helps the field flux. Damper winding flux actually help the field flux. If I write dW for the damper winding flux, then damper winding flux help the field flux. So, if we see from the point of view of armature reaction, who is creating armature reaction? Armature current or armature flux induced in armature, and who is opposing that one? Field flux and the damper winding flux, right? Now, when there is a situation of fault, then armature reaction flux is huge. So it is trying to die down the air gap flux. That means it is trying to die down its output power of the generator. Then what will be the tendency of the generator to maintain its output? So it will try to increase its field flux, which is constant, and it will try to increase the flux effectively, which will support the field flux. So that's why the damper winding will come into action. And so damper winding flux is considerable because the current is very high. This fault current, not the normal operating current. So actually what is happening? This field winding or damper winding is trying to reduce this armature reaction or armature reaction during the fault. So actually it is trying to reducing the armature reaction, means it is trying to reduce this effective resistance reactance of the arm, which is representing the armature reaction. What is XA? XA represent the armature reaction in the equivalent circuit. So field winding and the damper winding is try to reduce the armature reaction. So as if it is trying to reduce this armature reaction reactance or XA. So as if in the equivalent circuit, we may assume that there are two reactances added in parallel, so that effective reactance, if we write this one as XA dash, double dash, which is become less than XA, right? So these two field winding is due to the, these two reactance is due to the field winding, another is for the damper winding. I must mention here that these damper winding and field winding and the armature winding are totally separate thing. There is no electrical connection between them. But their behavior is such that in the equivalent circuit, we may represent that this armature reaction flux is reducing. That means this XA is reducing. Then if we want to represent that one reactance is reducing, that means some reactances is added in parallel to that. So that's why this is the representation to represent the behavior of the generator during subtransient position, because in subtransient condition the current is very high, twice the steady state fault current, and damper winding and field winding are in action, right? But they are actually, this is the representation of the behavior of the generator, but not the electrical connection, right? Like the whatever the leakage reactance, whatever the resistance is there, but whatever the ideal transformer we connect for the in transformer equivalent circuit, actually leakage reactance is not there, but leakage reactance is there, that is represented by the leakage. For representing the leakage flux, we introduce a leakage reactance in the equivalent circuit. In the same way, to represent the behavior of the field winding and the damper winding during subtransient condition, we are representing these two windings as in parallel to the armature reactance of the equivalent circuit. So if we draw that one, whatever I have told, that is written there in the previous slide. So this is the thing, but this is actually not the electrical connection. Due to the behavior of the machines, we can represent the equivalent circuit in this way. So in short, now this the equivalent of these reactances obviously will be less than XA, so we can write this one XA double dash, and total reactance we may write XS double dash. So in short, during subtransient period, we cannot represent the equivalent circuit of an alternator by this one, right? By this one we cannot represent, but we have to represent this XA by XA double dash, because in that case field winding and damper winding is trying to reduce the air gap armature reaction. So they are in opposition. So for that reason, we have to represent them. We have to consider them also. So for that reason, it will be XS double dash instead of XS. Have you understood this?
Yes, ma'am.
So in the same way, actually damper winding is for any short term crisis. So it has very short time constant. So within very short time, its flux will die down because it is a short circuited winding. And so if flux is dying down, then there will be no reactance. So it will be open circuited. So only field winding will be there to maintain its the armature air gap flux, although it is not possible. But still, during transient period, we may assume that only field winding is there, damper winding gets open due to its very low time constant, and at that condition, field winding is trying to maintain the air gap flux. So in that case, since it is less than XA, so we can write this one XA dash. So overall reactance will be XS dash. So in the during the transient period, the reactance will not be XS but XS dash, and obviously this will be the minimum value. This XS double dash will be the minimum value, then XS dash, and obviously field winding, the constant DC current is supplied from the field part. So it will have no capacity to maintain the air gap flux without further increment in DC current. But it will not be there because during fault condition, the armature, that control will not be there. That control will not be provided actually. So in that condition, field winding will be unable to maintain the air gap flux. Then what will be happen? The armature current will dominate. So in that case, during steady state, that the alternator will behave as its normal operating condition. It is like a steady fault current is flowing through it. So it is like a load current for the alternator, because alternator does not know whether it is fault or anything. It is no, it only supply if there be any connection at its output. So it will supply that huge fault current. So that all the power will be in vain, will be in the faulted path. So all the prime mover input will be actually lost. So this will be the thing if we allow the fault during the steady state period also. So the alternator has three different representation during three different period during fault. Then during subtransient period, the reactance will be xs double dash. During transient, xs dash. During steady state, xs. For the cylindrical rotor, for the salient pole, it will be xd dash, xq dash, xd double dash, xq double dash, xd and xq. So I hope you have understood this one. Any doubt? Now this representation of the alternator is same applicable for the synchronous motors, because they are same machines, only the direction of currents are opposite. So the same representation will be valid for the synchronous motors. Now what will be the representation of the transformers? The representation of transformers and the induction motors will be same. So for transformers, this is the transformer equivalent circuit referred to primary, and for a per unit system referred to primary or secondary will be same. Since the fault current is huge, this fault current is flowing through this transformer, then the no load component of current is very low as compared to the fault current. So we may disconnect that one, right? So it will be represented only by a series circuit, right? So now this, if we apply the pyronite representation, then we have no need to bother about the primary or secondary. We can use it very readily, right? So one more thing I have not discussed here, that is the representation of transmission line. I have already discussed that one during the representation of per unit system. Similar to the transformer, the shunt capacitance part of the per unit of the transmission line representation has very low contribution during fault. So we neglect that shunt part, right? But all these things we do for the ease of computation, nothing more than that. As in case of power system planning design, we have seen that for short line also we can use the equivalent T, equivalent pi, or nominal T or nominal pi, but we have not done that one, because that will only increase the complexity of the calculation, nothing more than that. In the same way here, we generally neglect the shunt part, because shunt part of the shunt components which have very low contribution in the fault current, we neglect that one, because here we need only an estimation of fault current. Now there are some terminology related to the fault calculation. One is fault current. What is fault current? Fault current means for current flowing through the faulted path or the shorted path. Then another is the fault MVA. Fault MVA is also called short circuit MVA. Fault MVA is the fault current plus into pre-fault bus voltage. Okay. So pre-fault bus voltage, if we know, then if we multiply it by fault current, we can get the fault MVA. Generally, we represent it in three-phase basis. So it will be root 3 VLIL or 3 VPIP. And fault MVA or short circuit MVA actually is required to calculate, to select a circuit breaker capacity of the system. Say if for a system, this is the fault MVA. Say if it is 130 MVA, then we shall select a circuit breaker with a capacity of 150 MVA or 140 MVA, not less than 130 MVA, right? So this is the steady fault current. Then there must be a transient rating also, subtransient rating also. That is depend on, that is called actually transient rating, but we consider the subtransient value, maximum possible value of current. So in that case, we shall take 1.8 times of the steady state current, and we shall calculate the short circuit MVA during transient condition. So in simply, it will be 1.8 of this. So short circuit MVA during transient condition or subtransient, during subtransient condition more specifically, it will be 1.8 times of the steady state fault MVA. Now, how to calculate the fault current? So at first you draw the single line diagram of the given power system. So for calculation also, it is better to take the per unit system, because it is an interconnected power system. There will be so many rise and drop in the voltages at different parts. So select a suitable base MVA and convert all voltages and impedance of the 1 minute. I'm coming. So then we have to select a suitable MVA and convert all voltages and impedance of the power system in per unit. That we have done in our per unit representation already. Then draw the reactance diagram of the power system and show all electrical parameters, voltage, impedance, all the things in the diagram. Then this part we have all 1 to 3 are same as we have done for the per unit representation, to draw a reactance diagram of a power system using the per unit representation. Then you have to identify the fault point in the reactance diagram and connect it with the reference. Why? Because we are calculating the fault current during the three-phase short circuit. So per phase representation will be same, and since it is three-phase to ground fault, so or three-phase fault, then the fault point is connected to the reference. Then calculate fault current using circuit theory and calculate Thevenin's equivalent circuit in between fault point and the reference. So you can use any circuit theory as well as the Thevenin's equivalent circuit also. Thevenin equivalent will give you the calculation, will make your calculation easier. Then all the fault current calculation will come in per unit. Then we have to convert it into ampere or kiloampere depending on the base current of that particular fault condition. Now if we say one example, can you hear me?
Yes, ma'am.
So if we assume one example, so this is a single line diagram of a power system, and there is a solid three-phase fault at the HT terminal of the motor transformer, right? So this is the motor. So near to the motor, this is the motor transformer. So fault is there. HT terminal is this side. So fault is here. Then it is asked that draw the reactance diagram of the network under faulted condition and calculate fault current. So reactance diagram part I have already discussed in per unit representation, so you can do it. I have given here, you check it yourself. Here I have considered the base MVA as 50, you can use 60 or whatever you want. Anyway, With that, if we get the per unit representation of the reactance diagram, so this will be the reactance diagram, right? Then we have to identify the fault point. So fault point is the HT terminal of the transformer. So this is the fault point, right? So fault point in the reactance diagram, if you see, so this is the transformer 2. So if I identify, if I mark this one, this point A, this point B, this point C, this point D, right? Then HT terminal of the transformer. HT terminal means this point. That means transmission line part of side of the transformer. So this is the uh, fault point, and we can connect it. We shall connect it to ground, and this will be the fault current. This is the thing. Have you understood? Have you understood?
Yes, ma'am.
Then I am asking something to you. Now you tell me, if I ask that the fault is at the generator terminal, that means fault at which point among the points I have marked in the figure? Fault is at the generator
Point
terminal.
A.
Hmm?
Point A.
A. And if it is the HT side of the generator transformer, HT side of the generator transformer, which
D.
point will it
D.
be? And the motor terminal, if fault is
D.
at the motor terminal,
D. D.
if I say the fault is at the middle of the transmission line, if I say that fault is at the middle of the transmission line, then we have to divide this reactance into two parts. Say, for example, point 1.14 and 0.14, right? I am this just in this way we have to separate instead of this part, right? Then this will be the fault point. We shall connect it to ground. Have you got it? Is it clear?
Yes, ma'am.
So here the fault point is the HT terminal of the motor transformer. So this is the fault point. Now if I apply the Thevenin equivalent, then we shall open this terminal, say F and N. Then obviously if we open this one, then open circuit voltage is 1 per unit. And the current we can calculate. If this is voltage is 1 per unit, this open circuit voltage will be the 1 per unit, and we can calculate Thevenin equivalent impedance. What will be the Thevenin equivalent impedance? Thevenin equivalent impedance will be the parallel combination of these two parts. So these two parts are there. So parallel combination of this will be ZTH. So from there we can calculate the fault current, right? Otherwise, by circuit solution also you can calculate that one. Now, important thing is that now we have to convert the fault current into the actual value. So, just I am diminishing that part. Now you see, so fault current we have calculated. This is the figure. So here fault was at the HT terminal of the motor transformer. So this side is 132 kV. The MVA is same 50, but the IB is the 130 VV is 132 kV. So and in that way we have to calculate the fault current, right? So at the same time, if I ask to calculate what will be the generator current at that moment, then obviously you can calculate this current in per unit, right? But in that case, when you calculate generator current in actual value, Then at this point, the voltage is 11 kV. So base current in that case will not be this one, but you have to calculate base current using the voltage 11 kV. So for the in the circuit, from the circuit you can get the all the currents in per unit, but whenever you are converting it into the per unit in the actual quantity, then you must identify what is the base voltage of that portion, because base voltage are different for different portion, different part of a power system. Have you understood? In this way, the it may be asked to find out the capacity of generators part side circuit breaker, motor side circuit breaker, transmission line side circuit breaker. What will be the fault MVA? So if you know the fault current and at any point, you can calculate the fault MVA. So whatever you are calculating for this particular example at this moment, that is for the fault at the HC terminal of the motor transformer. So it will vary with the variation in fault point. So fault current is 132 kiloamp, 1.24 kiloampere. So fault MVA you can calculate. So for this particular case, fault MVA is 289.93. At which point? At the HT terminal of the motor transformer. So if we install a circuit breaker at the HT terminal of the motor transformer, the capacity of the circuit breaker should be equal to or more than 283.93 ampere MVA, steady state capacity. Generally, capacity are the circuit breakers are available in the integer value, so it will be 300 MVA like that. Have you understood? Have you understood? I could not.
Yes, ma'am.
I do not actually understand whether you are listening to me or you are. I have disconnected
Yes,
or
ma'am.
not. If you do not respond now, there is one more issue. So in this way, we can. I have given only one example, because if you can understand this one, then you can solve any type of problem in fault calculation. So you must practice these things from the book, because there may be different types of problem in fault calculation. If I make a list of that, then I have to spend all the time in fault calculation. That is not required, I think. So I have explained you all the thing. You try the problems. If you have any doubt anywhere, then you ask me, or you can send me in email with your workout along with the problem. But you must practice this type of problems. So another thing is the enhancement of capacity of substation and its protection issue. Why enhancement of capacity is required? Due to enhancement in load, if the load is increased, then it is required to increase the capacity of a substation. That means generation capacity of a substation or incoming power capacity of a substation. So this is consider that this is an isolated substation. That is not interconnected to anything. So say there is a generator which has percentage reactance Xg, and these are the breakers, B for breakers. So two outgoing feeders are there. Feeders are called transmission line. In protection um, uh, terminology, it is always called feeders. This is same as transmission line. So if the load is increased, then we have to increase the generation capacity. So we may increase the more number of generators here, or we can connect it to grid through a transformer. Then also we can get the power from the grid. So in that way we can increase the capacity. So there are two issues. So the easiest one is to connect it with the grid, because actually this thing happens. All the power systems are actually interconnected. So it is connected through a transformer to the grid to match with the voltage level of the substation. Now you see Xg is in percentage, right? Percentage means out of 100. So we can whatever value in percentage, you can write whatever the decimal value that will be in per unit based on own rating of the generator. So what happened when we connect direct transformer here, direct grid here, then the capacity of the substation increase, but at the same time, short circuit level of the that bus will also increase. So if there is an increment in short circuit level of that bus, then obviously we have to change all the breakers. Say initially the short circuit rating was 130 MVA. We have connected the breaker of 150 MVA. It was safe. But now due to incoming grid, now short circuit MVA become 200. Now 150 MVA of the breaker will not work. It will not, it cannot save the system. So in that case, we have to change all the breaker, which is very costly and it will take long time. We have to interrupt load at that time. So the easy method is to connect the incoming power generation to a reactor. This will limit the short circuit current. At the same time, it will help to use the existing circuit breakers for the with the enhanced capacity. Say, let us discuss with the fault MVA. So when there was just isolated system, then the generator reactance was Xg. So in per unit, say it is X by 100. So if the reactance is, if we know the reactance, then we can know the calculate the per unit fault current, because here the voltage is 1 per unit. So the reactance is only one reactance is connected in between the bus and ground. So the current will be 1 by that reactance. So in that way, it will be 1 by Xg per unit. Xg here I am assuming in per unit. So how the whatever breaker is selected, that must be more than that short circuit MVA. So let us select, we have selected that one. Now when a grid is connected to the substation, then there through a transformer. So grid has, I assume that infinite impedance. It's actually zero impedance, sorry. So in that case, there will be there only on the transformer reactance will come. So actually it will be this fault MVA will be 1 by Xg plus 1 by Xt. Now this 1 by Xt is the additional part. So it may, due to this SF2, the new fault MVA may come more than the existing circuit breaker rating. I shall give you an numerical example also. So for that reason, it may not be possible to make the system safe with the existing circuit breaker. So in that case, we connect the incoming grid to a reactor. So in that case, this X will be added with this transformer reactance. So that will limit the incoming fault MVA, and that may adjust with the existing breaker rating of the system. Oh. So fault MVA is now this one, whatever I have explained with the reactance, the things I am not reading, that is for you. So if introducing current limiting reactor may make HB less or equal to the greater or equal to the SF3. So from there we can calculate what may be the value of X. That is the one numerical expression, the one expression. I am not going to that. Let us go for one practical example. Similar example with only the numerical values. One substation was there with the two generators. Generators rating are given, percentage reactances are given. But due to change in capacity, enhancement in the capacity, the grid is connected through a 10 MVA and X equal to 7.5% reactance to the system. To use this existing circuit breaker, one reactor is added, right? Existing circuit breaker capacity is given. Existing circuit breaker capacity is 150 MVA, right? Now you see, in absence of grid, when this grid part was not there, then what was the MVA, short circuit MVA? If we assume that base MVA is 10, then reactance of the generator we can calculate. This is 2500 kVA, 5000 kVA. This is 10 MVA. So base MVA is assumed as 10, right? So it is, if we convert in terms of 10 MVA, so 10 MVA. So then we can convert it into, it will be 0.32 per unit. Similarly for generator 2, it will be 0.12 per unit. Now what will be the equivalent reactance without grid? This will be some value. That is parallel combination of these two reactants because they are connected in parallel in the equivalent circuit. If you cannot understand, you draw the reactance diagram by yourself. Then short circuit MVA will be 1 by this because short circuit MVA in per unit and the fault current in per unit will be same because pre-fault bus voltage is 1 per unit. So it is 11.45 per unit. Now if we multiply it by MVA, directly we can get the short circuit MVA. You just note here, we have no need to bother about the the bus voltage, right? So it is 114.548. So it is quite lower than the circuit breaker capacity, or circuit breaker capacity actually on the contrary is selected in that way that it will be much higher than this. That's why circuit breaker capacity is 150 MVA, right? Much higher than 114.54 MVA. It is safe, obviously. Where if there be any fault in the system, then circuit breaker can save the circuit. Circuit breaker can break. Circuit breaker will not be affected because its MVA capacity is higher than the fault MVA. Now, if we consider for the grid section, the transformer has this much of reactance, so this will be the MVA. So total MVA will be additive. Now you see it becomes 247.88, much higher than 150 MVA. So if we do not use this reactance, then we cannot use this 150 MVA circuit breaker because circuit breaker will be affected. Affected with this 247 MVA if there be any fault at that bus, near to that bus. So for that reason, we need one reactance, right? So this reactance will limit the current with how much? Because actually 114.54 was there. So in our hand there was some allowance, 150 minus this one. So that allowance we may use for the incoming grid using this reactance actually. So summation of these two will be equal to circuit breaker capacity. So from there, actually, we can calculate what will be the value of reactance, and using the base impedance, what we can calculate what will be the actual value in ohm. So from there, we can calculate also what will be the value of inductor, right? So in this way, using current limiting reactor, we can limit the fault current, right? Have you understood?
Yes, ma'am.
So this is the end of short circuit fault. Next, I shall start in economic load dispatch, but not today because I am giving you the just 1 day gap. I think I have your class on Wednesday. So in the meantime, you go through the per unit system and the short circuit study. You go through at least the workout examples of any standard book, the books written in your syllabus. So if you have any doubt, then you tell me in the next class. Then from the next class, I shall start the economic load dispatch. Okay. That's all for today. You write your name and roll number in the chat.
Ma'am, is asymmetrical fault analysis not in our syllabus?
It is in your 4th year first sem syllabus.
Okay.
This is actually introduction of fault analysis. Asymmetrical fault analysis part will be covered in your 4th year first sem syllabus.
Okay.
It is there.